So we are finished with our discussion of ideal flows, and the next topic that we will discuss is boundary layers. So we're going to discuss here what happens when we cannot really fully neglect inertia, and when effects of viscosity start to become important, and we'll see that then they're only important in a small region around no slip boundary condition around solid interfaces. So we are going to discuss essentially four things in this boundary layer, and it will take us roughly 2 days. The first thing that we will discuss are scalings. So we'll derive first scalings for the boundary layer thickness. After that, we will derive the boundary layer equation. So we'll start from the Navier-Stokes equation, from the momentum equation, and see how they are transformed when we assume a boundary layer. After that, we'll look at one specific case, the most famous or the most well-known boundary layer, which is de Blasius solution to the boundary layer. And the Blasius solution corresponds to a boundary layer which is developing on top of a surface where there is no pressure gradient in the streamwise direction, so along the direction where you mostly have flow. So one way of thinking about this boundary layer when there is no pressure gradient is essentially to look at the boundary layer on top of a flat surface. And after that, we will discuss very crudely what happens when there are pressure gradients. Remember, sorry, if you are thinking about the flow on top of a sphere or the flow on top of an airfoil, from the leading edge to at first on the top surface you will have a pressure decrease, so your dp dx will be negative, and after that when the flow is decelerated, you have a positive pressure gradient. So usually along a profile or along a sphere or along any object, there will be pressure gradients in the streamwise direction. So we'll discuss a little bit of what happens when the pressure gradient is non-zero, and that will lead us to discussing detachment, separation. But first, let's summarize what we've seen so far. So when we wrote our momentum equation, we started in the first quarter discussing the Navier-Stokes equation, the momentum equation. So let me remind you, we have the rho times partial u partial t plus u grad u. That is the material derivative, and this is equal to the sum of all of the external forces, first minus the pressure gradient, which corresponds to the pressure force, which is a surface force, plus mu times the Laplacian of the velocity, which corresponds to the viscous term, plus our body force term. And in all of our discussion, the two terms that we often look at and compare are these two terms: the inertial term on the one hand, so the u grad u term, which is the nonlinear term in the momentum equation, and the viscous term. And so we discuss that you can characterize from non-dimensional analysis the relative magnitude of both with the Reynolds number, which is equals to rho u times L divided by nu. And what we did before is to essentially assume that the Reynolds number is very large. And when the Reynolds number is really large, that means that the inertial term, is much larger than the viscous term. And when the inertial term is much larger than the viscous term, and we cross out the viscous term here, so we assume this viscous term here is negligible, then the equations simplify to the Euler equation. And that's what we've been looking at for the past, since the beginning of the semester. But of course, we saw also that this leads to problems because, for instance, once you are at a solid interface, you cannot impose a no-slip boundary condition. And we impose a full slip boundary condition. You're just imposing no penetration boundary condition. But that is not realistic because we do know that there is some finite viscosity in any flows, and in any flow you cannot really neglect the effect of viscosity. Otherwise, you can't impose a no-slip boundary condition, and people have observed that actually there is a no-slip boundary condition. So where does that lead us? Well, let's look at when we non-dimensionalized, assuming the Reynolds number was large. Actually, the equation we got was the momentum equation was the following. So we keep all of these are in non-dimensional terms. So we have our inertial term here, our pressure term. Those are non-dimensional here, plus 1 divided by the Reynolds number times the Laplacian of the velocity. And of course, so we assume that because the Reynolds number was really large, we assume this term here would become very, very small, and therefore this whole term could be neglected. But if you think of it, this term includes terms such as the second partial of u with respect to y. And what happens if this term becomes really, really large? So if you're thinking about a very small boundary layer in which you have enormous gradients of the velocity, so when you have significant shear over very small distances, this term could become really large, right? And so if you have a large term divided by a large number, there is a region where this term is not going to be negligible. And the region where this term is not negligible, so where those two effects here balance each other, is called a boundary layer. So what we're going to do now is just to start by deriving scalings for the boundary layer, for the length scale of the boundary layer. So that's what we'll do, boundary layer scalings. So let's assume that we have an airfoil, right? First we'll reason with the length scales. And so if we have an airfoil here, that is the flow that we have, and let's say that the length scale of our airfoil is capital L, and we have an incoming flow, a uniform flow of velocity u. So this is our typical example for a uniform flow. What is going to happen is that around the no-slip boundary condition here, you will develop a small boundary layer where effect of viscosity are important. And what we want to find is a scaling for how thick this boundary layer is, this boundary layer here. So that's delta. We're going to call delta our boundary layer thickness, and we're trying to find the length scale for this region where the effect of viscosity and the effect of inertia are comparable. And so the idea would be that outside of this boundary layer, right, outside of this boundary layer, we find no viscosity, right? The effect of viscosity outside of the boundary layer are going to be negligible, and therefore outside of the boundary layer, we are justified in assuming the flow to be governed by Euler's equation. So what we want is to derive a scaling for the length scale of the boundary layer delta, over which the effect of viscosity will be negligible. So we have two terms. We have our inertial term and we have our viscous term in the momentum equation. And so we're going to try to derive scaling for both. So let's start with the inertial term. So this is the u grad u term. We have u grad u, and so we're looking at the inertia, and most of inertia effect take place along the x-axis. So if we're thinking about what is the largest length scale over which u changes, what is the length scale over which the velocity u changes, the velocity mostly is in a stream direction, so this would be along the x-axis. And so u scales with u, and the gradient, I don't know why this is happening, and the gradient of u scales with L, with u divided by L. So we can here find a scaling for the inertial term, which is rho u squared L. We've done this scaling before. Now let's look at the viscous term, which is mu times the Laplacian of u. Now in this term, we have the sum of three terms. We have the second partial of u respect to x. We also have the second partial of u with respect to y. And if we assumed a 3D flow, we also have the second partial of u with respect to z. But let me forget about this for a second, and we'll just compare the second partial with respect to u, to x, and to y. So the characteristic length scale along the x direction is capital L. So the first term will scale with mu times u, the velocity scale, divided by the length scale in the x direction, which is L. Right, so our length scale here is L squared. However, the other term, partial u, partial y squared, will scale with mu u, but the length scale now has changed because we are looking only in this small region. And so here, we're looking in the region where there might be shear. So this region here scales with mu u delta, or divided by delta squared. But if delta is very small, then this term here is small, so this whole term is going to be really large. And if L is much larger, then u divided by L squared is going to be much larger than the other one. So one of these two terms is negligible, and this is the second partial of u with respect to x. So we can neglect this compared to the other term. So if we want to find a scaling for delta, then we simply have to say that in this region of thickness delta, these two terms are comparable in size. So when do viscous terms become important in our Navier-Stokes momentum equation? It's when these two terms are of similar scaling. So if they are of comparable orders of magnitude. Okay, so we're going to write that. Let's assume that our inertial term, rho u squared divided by L, is roughly of the same order of magnitude that our viscous term with the partial with respect to y, so mu u delta squared. Right, so we can deduce a scaling for that for delta squared. So we're going to extract delta squared here from our scaling, and that leads to delta squared, which will scale then with rho u. It will scale then with mu u L divided by rho u squared, which we can simplify, and that simply gives us mu divided by rho u times L. Now, if we want a scaling for delta, let's make the scaling. Let's compare delta relative to the length scale L. So we'll derive this by L squared, and we'll get that delta squared divided by L squared scales with mu divided by rho u L. So now here we have our scaling. We simply need to take the derivative, the square root, and notice that this number here is the inverse of our Reynolds number. And therefore we can write that the length scale of the boundary layer delta divided by L scales with the square root of 1 divided by the Reynolds number. Now this here is our scaling for a laminar boundary layer. And what you see indeed is that when the Reynolds number is large, so when Reynolds number becomes really large, then 1 over the Reynolds number becomes small, and this boundary layer becomes small. So when the Reynolds number is large, the region over which the effects of viscosity are important is a region of very small thickness. Now we're going to continue our discussion on scaling, but this time we will reason in terms of time scales, and we'll think about the boundary layers not in terms of the viscous term and the inertial term, but we'll think of it in terms of vorticity. So let's look at these time scales and assume a very simple flow geometry. So we have a flat plate, and now we no longer assume the flow to be inviscid, so we are going to have a no-slip boundary condition on this flat plate here, and we have a uniform flow. And what we'll assume is that essentially here we don't really want to know what's happening here, so let's assume there's no flow here, and that we have an infinite uniform flow coming in, and we turn on the effect of viscosity at this point. And the question we are going to ask is, so here the flow is irrotational in all this region, right? It's uniform, but here we impose a no-slip boundary condition, so somehow there is going to be vorticity created at this no-slip boundary condition, right? And one thing is to realize that, well, it is possible that it is not possible, but because of the vorticity equation, the vorticity is going to be transported to from the surface of the no-slip boundary condition to the bulk. And so one way of thinking about the boundary layer is to think of it as the thickness on top of a no-slip boundary condition over which you will find vorticity, and elsewhere you can assume that there is no vorticity. So let's think about vorticity. We've discussed that before. At the solid interface here, at this solid interface, we will create vorticity. And so the question we're going to ask is, let's assume that we are at a point X along the x-axis here, and the question is up to where at this point, how far into the bulk of the flow has vorticity diffused, right? So it's, of course, it's not really like that, but let's think that we have two regions where the flow is rotational, there is no vorticity here, and where there is vorticity. How can we approximate the thickness here over which vorticity will have diffused? We'll have permeated the viscous penetration depth, if you want, of So remember that at this interface we have a no-slip boundary condition. Because of the shear, and therefore we have creation of vorticity at this boundary here. And if we have the first mode of vorticity that we've diffused, that we've discussed, is diffusion. So the vorticity is going to diffuse, and so from being created at the interface, the vorticity is going to start to penetrate inside of the flow domain here. So the vorticity is going to start to enter the flow domain via diffusion. And what happens next? Remember that vorticity is also transported, is also advected. So we have a uniform flow, which all of the vorticity which is created here and starts to diffuse is then going to be advected downstream. Right? So we have that the vorticity is going to be advected with the velocity u. So with that, we can think about the scaling, right? Because how long does it take, if we are at this distance here, x, how long would it take for vorticity created at the wall to diffuse all the way up to a length of delta, a depth of delta? This we've seen before. This is this delta scaled with the square root of the diffusion coefficient, which in this case is the kinematic viscosity, times t, times the time scale. So this thickness here, right? How long does it? How long, if I'm giving a time t, how long? For a given time t, how far will have the vorticity diffuse inside of the bulk? It's delta scaling with the square root of mu times t. And if you're thinking about this point, how long did the vorticity have time? What time did it have to diffuse to that? Well, you have to think that the vorticity which is here was created here. So it was the vorticity created here, which diffused a little bit into the bulk and then continued diffusing while being advected and eventually ended up here. So the time scale for this process will be the advective time scale. So it would be x divided by u. So if you replace this time t by x divided by u, you get a scaling for your boundary layer. And you find that delta x now will scale with the square root of mu times t, which is just x divided by u. So we'll scale with mu times x the square root of mu times x divided by u. And note that this scaling is equivalent to the other scaling that we had when we looked at length scale. Because if we assume that x is at the very end of our profile, so if we assume that x here is L, then we just have to look at so this is equivalent, to the other scaling. and we just have to replace x by L, and we find that delta L is equal to the kinematic bound viscosity is the dynamic viscosity divided by the density. So it will be equal to the square root of the dynamic viscosity divided by the density times L divided by U. And so if we divide everything by L, we get again the square root of 1 divided by the Reynolds number. And here I'm putting a subscript L to indicate that it's the Reynolds number which is based on the length scale L. We can also see from this expression here, you see that delta x has a square root function, and this is why you always draw your boundary layer that has sort of a shape of the square root, right? The shape of the square root is essentially shows you that you have the competition between two phenomena. You have the diffusion of vorticity from the wall, right? And you have a transport in the x direction, which is advective.